Okay, in this talk, I will show how you can process reconstruction models using DIPY. For this, I prepared some notebooks that you can find on my repository, GitHub Rafael NH, under the repository DIPY Workshop 2021. So if you open, you will find here some notebooks, and please feel free to try to run them yourself. And if you have any issue on running them, please drop me a line and I will be happy to assist you. Okay, so I have opened the first notebook. So for the people that don't know what is a Jupyter notebook, this is a useful way to show your code. So for example, this allows to have shells to introduce some comments. So here I'm adding some comments about what is diffusion or Kurtosis imaging. And also it has shells where you can introduce code. To switch a shell to code to nodes, you just go to this option here in the code represent shells to code, and Markdown will change the shell to just comments. So I will do this here. I select the shell as being a Markdown. So if now I do a shift enter, this will become a string, a comment. So returning this to the code, okay? And this is now some lines of code that I just processed. Okay, so what is the first thing that you have to do in DIPY to fit your data? So the first thing that you have to do is load your data. Here in this example, and as we did on the previous talk using the command lines, terminal command lines, we download a multi-shell data for DKI fitting. This can be done from functions of DIPY data and using the function get fnames. So here I'm fetching the same multi-shell data set here. This function might take some time to download the data. However, you only need this to do this once, and the second time that you will run this, this function will just return the directories where your files were saved. So here below, I'm printing where the files are saved, and basically this loaded data set has to contain 3 files for diffusionmri processing. The first one is a nifty file containing the 4-dimensional data of your diffusionmri data. Then you have a file containing the b-values corresponding to your data, and a bvex file containing the gradient directions. It's important to note that if you don't want to use some data that's DIPY provides you, but you want to try to fit your own data, the only thing that you have to do is just to define these variables with the names of the paths where your data it contains. And so again, you need to provide a nifty file, your b-value file, and a file containing your b-values. Okay. So now that you save the directories, you can read your data to variables, and this you can use functions from DIPY-EO. And here, so we are loading the raw diffusionmri data, and using the read b-values bvex, you can read your b-values bvex files. Okay, so one important thing in DIPY is that it assumes that so many of the codes use this gradient table object. And what is this gradient table object? Basically, it saves your b-values and b-vectors on the format that is compatible with the code. And it's also very useful to summarize several diffusion parameters in a single object. So here we do this. So this can be imported from DIPY core gradients, and we inputted our variables containing the b-values and b-vectors and produce this GitHub object. So then the second step that I do before fitting is to do some preprocessing. And here what I'm doing is basically computing a simple brain mask. Okay, so the same Medium-Watson function that I showed on a previous talk using the terminal command lines. And this can be imported from DIPY segment masks, and I'm importing the Medium-Watson field. Okay, so diffusion kurtosis imaging, as I explained on the last talk, requires estimation of a large number of parameters, and also it captures deviations of the log signal decay. And this information can be a little bit hard to capture because sometimes these deviations are very slightly. So you really, recommendation is you really need to carefully preprocess the data to remove possible artifacts, also try to suppress noise. So here in these cells here, I'm just applying a PCA denoising technique, but I will not go in deep details here because on the next talks or in one of the following talks, you will have series who will present different denoising techniques on DIPY. And please feel free to use here your favorite denoising technique or preprocessing techniques. So now that we've preprocessed the data and we have the mask, we can fit the models. And in DIPY, fitting models always have a similar recipe. So all the models can be reported from DIPY Reconstruct. So here for a reference, I'm importing first the DTI model. And so the following recipe is then you need to define the model according to your acquisition parameters. So this is by calling an object with the name of your model. So in the case of the DTI, it's a tensor model. And so you define DTI, you import the DTI, then you define its model, and you input it the gradient table, and this will generate the model according to your acquisition parameters. Then, after you define this, you can fit your data. So then you can just write your the tensor model objects that you define, and you will have this attribute, which is a function, to fit the data. Okay, so here I'm giving the processed data and the mask. Okay, after fitting this, then you can remove the statistics parameters from the TensorFit object. So here I'm extracting the FA, the MD, the axial diffusivity, and the radial diffusivity. For DKI, it's again the same recipe. So you have to import DKI from DIPY Reconstruct. Then you have to define the diffusion kurtosis model based on your acquisition parameters. And then having this defined model, you can fit your data. And here I'm fitting the FA, MD, axial diffusivity, and radial diffusivity from the DKI, and also the standard mean kurtosis measurements, such the mean kurtosis, axial kurtosis, radial kurtosis, and kurtosis FA. Okay, so here in this shell, I'm just plotting some of the data. And basically what I'm showing here is a comparison between the diffusion parameters extracted by kurtosis and the diffusion parameters extracted by DTI. And you see that they show similar contrast. However, the DTI will show lower values of diffusivities. This is expected because, as I explained in the talk, DTI doesn't assumes that the signal decays linearly. So if you have a deviation of linearity and you force to have a linear decay, you will underestimate the diffusivity. So it's why they show here lower, while in the kurtosis, you kind of correct the diffusivity value. So it's another advantage actually of DKI is that you can have more accurate estimates of diffusion parameters. So then here I'm showing the standard metrics of kurtosis, and this is exactly the same figure that I showed in the slides. And finally, I'm showing how you can process the mean signal diffusional kurtosis imaging. And this has to be done in a separate model. And why is this? Is because this doesn't uses the information of the signals at each direction, but use the average mean signals. So here, you can call the mean diffusion kurtosis model from DIPY construct. Again, you have to define it using the gradient object. Then you can fit your data. Here I'm showing the mean signal kurtosis index, and I'm plotting here in comparison with the mean kurtosis. And this again is the slide, the figure that I showed in my previous talk. And you see that the mean signal kurtosis has a higher robustness, not showing the black box of artifacts as the mean kurtosis does. So this notebook was produced based on some examples that are present on the DIPY page. So if you want to know more information, also I recommend you to give a look to this examples on the DIPY website. So you can just press and it will indicate to there. Okay, so that is all, and I want to thank you for your attention.